what we're now going to do is really try to check that this vector is, when you repeatedly apply r, it stays in some two-dimensional plane. And what's really happening is it's rotating by 60 degrees within this plane. So now you have to maybe think back to your homework or something I've like briefly mentioned in class, which is, if I give you like some weird, unitary operator and some weird vector, and I kind of tell you like, hey, I think this vector is, in one of the planes of rotation, how do you check that? And maybe you remember, like if I give you some vector and I apply the operator to it, the unitary, it goes somewhere. And if I apply the operator again and it goes like this, then it's not like in a 2D plane of rotation. But the case where it is in a 2D plane of rotation is like you take the vector, you apply it, and you apply it again, and you get something that's like, well, sort of still in the same 2D plane. So you like apply it again, you're still in the same 2D plane. And the way I told you can check it actually is like if you take this vector, sorry, this marker is not very good. Take this vector, I don't know, call it v, and then like you apply some unitary u to it, and you get to uv. And then you apply it again to get to like uv. If this middle vector is like parallel to the average of these two vectors, that's exactly the case where like everything is happening in a 2D plane. Or like if it's parallel to like the sum of these two vectors. That's the case where v really is in a 2D plane of rotation for u. Or like where this one is a linear combination of these two, or like equally well, the middle one is a linear combination of the first and the third. So that's what we have to check now. So claim, 1 is that this special steering wheel vector is in one of R's 2D planes of rotation. And the way we're going to check this is we'll check this by checking that if you do r to the steering wheel state once, it's parallel to the sum or the average of the basic steering wheel state and the 2 times applied r to the steering wheel state. Okay, so I hope you agree, and you can ask if you like that. If we can do this, that does indeed verify that like when you repeatedly apply r to the state, you're always staying in like the span of, these two vectors or these two vectors. This is like a homework problem. And this is not too hard because we can just do it sort of visually. Hopefully. Okay, let's try to use 3 colors here. Okay, so for just this one, steering wheel 60, it's like horizontal, and then it ticks around by 60 degrees. So 60, 60, 60, 60, 60. Okay. And then we'll do the 2 times one here. So it's like we shift this down twice. So this horizontal will go to here to here. So this horizontal gets to here. This diagonally down gets to here. And you see it's kind of like it's shifting around 60 starting from here. So it'll be like here, and then here, and then here. Wait. Oh, I always get this wrong. Here, here, here. I used to do this with 5 instead of 6, and sometimes it's a lot easier with 5 to draw. Anyway, okay. And finally, let's look at this one. So again, we'll start with the red one, and we'll just shift it down like one step. That's what's going on with R. So we step it down one step, and this horizontal guy goes here, and then it's here, 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 here. Okay, so as you can see in this picture, the purple vector, the middle one, we applied R one time. It's exactly, basically parallel to the average of the red and the blue. So like it's true in each of these columns. So it's true like in general that if you like average the whole red vector and average the whole blue vector, it points in the direction of the purple vector. Okay, so we did it. We did this claim. Okay. Great. Well, what's next? Okay, so now we know that this vector, if you apply R to it repeatedly, it rotates in some two-dimensional plane. But what angle does it rotate by? Now you might say, like, obviously 60 degrees, right? But this is also not actually obvious. Like, it seems true, but we really also have to check this. So, okay, how can you check that? Well, the way to check that, I suppose, is to take the steering wheel state, apply R one time. So like, let me draw the diagram over here too. This is like some high dimensions. We start with the steering wheel state, and then we apply R one time to it. And if we don't know anything, we want to know, like, hey, what is this angle? Well, the thing to do is try to compute the dot product between these two vectors. And if the dot product is cos 60 degrees, then you say, hey, great, that means the angle is 60 degrees. So let's try that. So claim R rotates this steering wheel vector by theta, which is 60 degrees. Okay. Well, whatever theta is, we know that cosine theta is equal to like the following dot product. It's like the dot product of the steering wheel, well, R applied to the steering wheel state and the steering wheel state. Actually, this is not quite right, because I didn't mention it before, but I'll mention it now. The steering wheel state is not normalized. It's not a length 1 vector. Actually, let me ask you, what is the squared length of this vector? Imagine, it's really this 12-dimensional vector. What is its squared length? Uh-huh. 6, that's right. So this, remember, let's dial it all the way back. This stands for a 12-dimensional vector. It's got 12 entries, numbers. And the squared length of this vector is the sum of the squares of the entries, or the dot product of it with itself. So we got to do the sum of the squares of the entries here. Well, remember this one also, this is like the unit vector. This is like 0, 1. This is, I think it's like negative, no, it's like root a quarter, negative root 3/4. It doesn't matter. But this is whatever it is. It's something, 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 something. And now we just have to compute the sum of the squares of these 12 numbers. Well, this squared plus this squared is 1. And this squared plus this squared is 1. And this squared plus this squared is 1. This squared plus this squared is 1. This squared. So they're all sum up to 1. So we get like 1, 2, 3, 4, 5, 6. OK. So let me just write that down so we don't forget. Squared length is, well, L equals 6. Okay, so therefore, I guess length is root L, which is root 6. So let me write a twiddle here so that this means the unit length vector. Just the scaling of it. So that's like, I guess it's like root 1 over L, which is 6 in this case. Okay, and we really want to use the unit length version because then we can say like, oh, the angle between these two unit vectors has the property that like cos theta is the dot product of these vectors. That's how dot products work. Okay. So actually, I mean, we can get it back to maybe how we liked it better, where we didn't have these twiddles up here, because like this introduces a factor of 1 over square root L. This twiddle introduces a factor of 1 over square root L. These are just scalars, so it comes out, and we get like 1 over L times what I had written before. So the dot product of the steering wheel vector and the steering wheel vector applied with R applied. Okay, and now, again, we can just endeavor to do this. So we're dot producting two vectors, this vector and this vector. So let's just write them down. We're dot producting this vector, which is right there. I'll try to draw it again. It's like a horizontal 60, 60, 60, 60, 60. And then this vector, we get by like shifting everything down the railroad track. So it's like here, 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 and here. So we're like, dotting this top thing with this bottom thing, and then also times 1 over L. Okay. And how do we do a dot product? Well, again, these are like 12 numbers. This one, this one, this one, this one, this one, this one. And this is another 12 numbers. This, 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 this. So we like multiply them together in pairs and add them up. So in particular, we do like this first column dot this column, and the second column dot the second column, this dot this, this dot this, this dot this, this dot this. And we add up those 6 dot products. And then we divide by 1/6. So what I want to say is that this is the average dot product of the 6 columns. The 6 columns. Does that make sense? Okay, so let me ask you now, what is the dot product of this 2-dimensional vector with this 2-dimensional vector? Sure. Cosine 60, that's right, because this vector and this vector make a 60-degree angle, and they're unit vectors. So their dot product is cos 60. And what's the dot product between this one and this one? I know you can do it. It's also cos 60, right? Because this is like, these two also make an angle of 60. These two make an angle of 60, 60, 60, 60. So all these little 2x2 or 2-dimensional dot products are all cos 60. So their average is also cos 60. So this is like just the average of 6 copies of cos 60 degrees. So the average is cos 60. So that means that cos theta is cos 60. So that means theta is 60. It might feel weird to do this because even every time at the start I'm like, isn't it somehow obvious that it's rotating by 60 degrees? But I don't really know a way to prove that except by doing this. Okay, good. So together with these two claims, what we've discovered is we've discovered one vector that is in one of R's planes of rotation. It's in the plane of rotation that's like 60 degrees. And yeah, so we're like 1/12 of the way there in some sense.